So we started talking about vectors. We're going to continue to talk about vectors today. And remember the boldface versus the arrow on top of the vector kind of business notation. And we talked about adding and multiplying vectors, adding and scalar multiplication of vectors. And the subtraction is kind of like addition and a scalar combination by scaling with -1. So between addition and scalar multiplication of vectors, we have some properties that will be important for us to try to remember. And these are vectors in any dimension, n-dimensional vector, for example. And these properties should hold. We have the commutative property, switching the order. We have the associative property and grouping. We have an addition by 0. Now notice the 0 there. The 0 is boldface. And it's important to look at 0 in this scenario as boldface because I want you to be able to distinguish between a 0 scalar versus a 0 vector. And here we have a 0 vector in Rn. And so this property is called an additive identity property. And the next one is the opposite. That will give you the additive identity. When you add two things, you add one vector and the opposite of the other vector. This is called the inverse property for addition. And then now we introduce the idea of the scalar multiplication and the addition, and we have the scalar is distributive, and the distribution kind of goes both ways with scalars and with the vectors. So you can distribute a scalar over several terms, several vectors, or you can distribute a vector over several scalars. So the distribution rule usually is a combination of addition and multiplication. And so the multiplication here that we're considering is the scalar multiplication. Because we haven't really defined a way to multiply two vectors together. And unfortunately, or fortunately, we won't see that until later on in the semester. And the only multiplication that we'll have for vectors is the dot product, which we'll consider the inner product. But like I said, it's not going to be seen until later on in the semester. And for those people that have taken physics and Calc 3, there's a cross product that we will not do in this class. Yes. Later on. In this class, yeah. And you know, the tricky part about this is that we're kind of introducing vectors as matrices, and so we're actually going to define matrix multiplication before we define the dot product. So, in fact, that's how the dot product is going to be translated in our class, is through matrix multiplication. But we haven't gotten there. Right now, we're kind of focused on scalar multiplication only. All right, the next one is kind of an associative property also, but an associative property that combines scalar multiplication. So I'll put associative property here in quotes. And then usually the multiplicative identity is with the regular multiplication, but in this case it's a scalar multiplication, so I'll also put that in quotes. Traditionally, this has been called the multiplicative identity. But since this is a special case, it's I'll put in quotes for scalar multiplication. Notice the one is not a boldface one, it's a scalar one, and that's important to identify. So you have to look at these things and make sure you know that what you're dealing with is a scalar or a vector. Generally, we don't make one into a vector unless you have something special in mind, like a whole vector full of ones or something. But in general, we don't do that. But the zeros, sometimes a zero can represent a vector, sometimes it can represent a scalar, and in fact, sometimes it can actually even represent a matrix. And so we want to be able to look at the zero and be able to tell whether that's a matrix or that's a vector or it's a scalar. All right. Continuing on with this idea about addition and scalar multiplication, we can combine a whole bunch of vectors and scalars and scale each vector and then add them all together. So when we do that, we have what's called a linear combination, and this phrase is going to be very, very important for us. The idea of a linear combination just means you take the vectors that you're talking about. There's a linear combination of vectors. You take all the vectors that you're talking about, and then you scale each one, and then you add them all together. So whenever you can express that quantity or that expression, then you have what's called a linear combination of vectors. So here's an example down here. Let's see if we can write this as a linear combination. Generically, we can have a linear combination of two vectors by arbitrary constants like C1 and C2. So, example of a linear combination, it can be your y vector is equal to C1 times U plus C2 times V, or C1 times minus 1, 2 plus C2 times -3, -1. That's all. Yes. Sometimes they call it weights because that's how I don't know where it started from, but in statistics they call your weighted average. And what you do is you have your expression and you multiply it by some sort of value to weigh that. Like your GPA, if you got 3 A's and 2 B's, then all your A's will be weighted with 4.0, and then all your B's will be weighted with 3.0s, and then you would add them all up. So the weights are the constants that are adjusting the value of the vector. That's just the name. Yeah. Well, the vectors have to be the same dimension. So the vectors all have to live in the same place. In other words, I can't have a linear combination of two vectors in R2 and then one other vector in R3. I can't do that. So they all have to be in the same dimension. But the scalar is a scalar, so it doesn't matter. I mean, there's no dimension to that. You could, then you can explicitly write that. I'll put sub 3 over here as -1 to 0, which means you added another dimension to that. So you can do that. And if generally, like in Calc 3 or something like that, when you're doing multivariable, you're examining things in 3 dimensions, it's easy enough to take a 2-dimensional vector and say, oh, it actually lives in 3D, but then we just put a 0 there. But if you're strictly working with R2, then it's better to just stay in R2 without the zeros. Okay. So a more specific example, instead of being so generic, let's multiply u by 3 or something, and then let's multiply v by -2, and let's try to see how that's going to look like. And then we'll see if we can take a look at the geometry of this. Is there a question? Well, it's a vector, so it has a direction and magnitude. So it's an arrow. It's not quite the magnitude of the vector, because the magnitude of the vector is the length, right? It's scaling your vector to a different magnitude. Yeah, I almost want to. When I typed this in and I said weights, and then because that's what it says in the book, and I almost scratched it off and just put coefficients. But constants, coefficients, I think either of those other terms would work in this scenario. If you guys have an issue with weight. I do. I just went to the doctors and she said I had an issue with my weight. Yeah. Oh, when I do stuff in class, like with my pen, I'll use the arrow. But when I write the notes, and also in the textbook, you'll see it's bold-faced. Yeah. Yeah, it's hard to be consistent, and I think the main thing is that they like the arrows bold-faced, but then when you're writing it, it's hard to bold-face something that you're actually writing. Oh, so we're back to this scenario over here. So we can have 3 times -1, 2 plus -2. I don't know, minus -2 or -2. Sorry. Either way. And so the operation is, I mean, it's clear what the operation is. You scalar multiply and then you add. So -3 and 6 plus +3 and +6 and +2. Then this is going to be 3 and 8. Okay. So just to give you a preview, a more meaningful use for these linear combinations would be the idea of trying to figure out how they might look like in 2 and 3 dimensions, and then generalize this to say, well, I put 3 and -2 for C1 and C2. What if I stay generic and just call it C1 and C2? Which means, what if I let C1 be whatever I want, and what if I let C2 to be whatever I want? So there's something interesting that happens when you say, I'm just going to let C1 and C2 to be whatever. And for that, see if we can visualize this. That's why we're doing an example where we have a 2 vector or a vector in R2, so that we can possibly try to see what this is going to look like. So vector in R2, the first vector u is -1, 2. Do that in blue. -1, +2. And then the other vector is -3, -1. -3, -1. And then in our particular example, we said let C1 be equal to 3. So we're going to take our u vector and scale it by 3. So I'm going to go, oh, how am I going to do this? No, it didn't stay. Didn't I have this problem? I can't just paste. There it goes. So remember the addition idea of scalar multiplication means you're going to extend your vector. And then the idea of addition is to find the parallelogram and find the diagonal. So let's take our second vector over here and no. And then we'll multiply that by -2. And so that's going to look a little bit differently from what we had. Oh, we have to turn it around. 1. Excuse me, I'm just having fun with my program. Anybody know how to rotate this? No. I'm used to that twisty thing, but it's not here. Anyways, let's just go with this. And so this is actually -2v. And then so if we do the addition, then we would draw that parallelogram. And then we have this vector now, 3u minus 2v. Okay, but that's kind of not what I wanted to do. I wanted to do something else because I wanted to make the C1 and C2 generic. So imagine, what if I let C1 equal to 1 and C2 equal to 2, or C1 equal to 1, C2 equal to 1, have them both equal to 1, and then have them both equal to 2, and then have them both equal to 3. What do you think that's going to look like? A weird slanted grid. So I'd go with everything except for the weird part, because it's not so weird. But what you could possibly have would be this slanted grid. That could span And I'll use the word span here as a foreshadowing, a preview, another word of the word span that we're going to use later. And it looks like it could span the whole xy plane, which is to say that there's, if I randomly pick a point in the xy plane, I can somehow get to that by scaling these two vectors in the appropriate way, which is kind of an interesting idea. And again, that's a little preview of span, but the idea of a linear combination kind of gives us a grid that instead of having the x and y, in your nice perpendicular grid, graph paper that we have, our grid can be based on two different vectors that are not necessarily perpendicular. I don't know if these two are perpendicular or not, but they may not necessarily perpendicular, but then they can span a whole slanted. With a slanted grid, they can cover the whole plane. So that's an interesting idea that we're gonna uncover later on. But for now, the idea of a linear combination just says you have a vector or you have a set of vectors, you're going to scale each one and add them all up, and then you'll end up with another vector. Okay? All right. Now, what we're going to try to do is try to tie all these ideas of vectors up with back to our first topic this semester, which was, I think, systems of linear equations, and then coming up with the coefficient matrix and augmented matrix and stuff. So what we want to do is we want to see if we can tie all that up together. So here's another definition. We have vector equations. I don't know if that's a definition in the book, but we can think about a vector equation as a linear combination of something equal to a specific vector. And so on the left-hand side, we see a linear combination. We have our weights of the vectors as x, and then we have just a random vector on the right-hand side that we should know as y or as b. So they say that this has the same solution set as a linear system whose augmented matrix is equal to whatever this is equal to. Okay. So let's take as an example, let's take the problem that we are working on. What was u again? -1, 2, and then v, -3, -1. And what was our answer at the end? 3, 8. So let's use this as an example and see if we can just play around with this, write it in vector form, and then write it in matrix form, and then maybe even eventually come up with a system that we're looking for. So the question might be, the vector equation that you might pose here would be, what values of x and y, x1 and x2, I suppose you can use x and y. We'll use x1 and x2. So we can set up an equation, a vector equation, to say what value of x1 and x2 do I multiply u and v by to get b? Now we know the answer because we made up that problem in the previous page, but let's just walk through this and examine it and make it look like a vector equation and then make it look like a matrix. So our vector equation will end up looking like, well, we can expand this or just write down the actual vectors that we have. So we have x1 times negative 1, 2, that vector, and x2 times the v vector, which is negative 3, negative 1, is equal to 3, 8. So that is your vector equation. And what they're saying is that you can rewrite these as columns. The vectors and then even the b vector as columns. And so that translates our vector equation into this augmented matrix, negative 1, 2, negative 3, negative 1, and I'm writing them and saying them in columns. Usually when I write matrices, I do the rows, but here, since we're looking at them column by column, we can think about them as columns. And then the augmented part, dotted line or no dotted line, as long as you know it's an augmented part, it's okay. Then your equation would look something like this, your matrix. And then you can turn this into a system of linear equations, right? And so what you are really solving for here is negative 1 times x1 minus 3 times x2 equal to 3, and 2x1 minus x2 is equal to 8. So here is your system of linear equations, 2 equations and 2 unknowns. Who says? Well, when we have a matrix, well, this is what they're saying here. They're saying that you can write your vector equation into a matrix. And now we've known that if we have an augmented matrix, we can go back and write that as a system. I mean, before we can say if we have a system, then we can write that as an augmented matrix. And we kind of went back and forth with that idea before, but now we're introducing the idea of a vector equation on top of that to say, hey, these are all the same thing. And yes, these are all the same thing. So your solution to your system can be solved with any of these. Well, I have the matrix form over here. Can we just do a quick, I don't know if there's anything quick, a quick row reducing. Let's say I want to multiply the first row by just 2 and add it to row 2. So that'll get rid of that, and then I have whatever this is, 2, negative 6, negative 5. What? Negative 7. 2, 6, 14. Thank you. 14. Yeah. So we can reduce row echelon form it. I just made a new verb. Or you could just solve it from here and just doing some back solving. So if you have negative 7x2 is equal to 14, we have x2 is equal to negative 2. And then you put that into the first equation. Negative x1 minus 3 times negative 2 is equal to 3. And we should get x1 is equal to 3, which is the solution that we already knew because we made up this problem in the previous page. But in any case, if we had this vector equation that we're trying to solve for and say this is u and v, these are known vectors, and we want that to equal to 3, 8. What should I scale the first one by? What should I scale the second one by so that we can have this vector equation to be true? We can transform that into our matrix, our augmented matrix, and solve. Okay, which, by the way, we also solve that system. All right, there's some exercises that I picked from the book. I stole from the book or used from the book. And I just want to do one of each, maybe number 9 or 10. It says here, write the vector equation to an equivalent that is equivalent, what? Write a vector equation that is equivalent to the given system. So we want to write this into a vector equation. So wait, before we do that, let's take a look at the relationship between the vectors, the matrix, and the actual system. So if we take a look at the system, the coefficients of the x's, right, -1 and -2, kind of match with the columns of your augmented matrix. Uh-oh, it's going to be all semester. And that in turn happens to be the first vector, right? It's not a coincidence. And likewise, the coefficients, the columns, and the vectors all match up. So what I'm trying to do here is kind of skip some intermediate steps, and instead of trying to write this in matrix form first and then into a vector equation, why can't we just see it as a vector? And it kind of follows that the coefficients or the unknowns x1, x2, and x3 correspond to the specific columns, the x1, x2, and x3 columns, or not x1, x2, x3, but the 1, 2, 3 columns. And then our last one over here looks like it's just your vector b. Uh-oh, can you see that now? Yeah, you can still see. So anyways, an intermediate step would be trying to write this into a matrix first, but let's skip that step and just say, okay, this can be written in vector form, vector equation form. x1, remember x1 is this, exactly what this variable is. It's not a vector, so I'm not going to put a arrow on top. And then it's multiplied by the vector what? 4, 1, 8, right? Just the coefficients. And then we can go along and just finish the rest of this. Note the negative signs. And then that last column turns out to be that b vector. Nine, 2, 15. Okay. Any questions? All right, let's do the next one. The next one is asking us if, so these are all linear combinations of something. They're asking us if B can be written as a linear combination of A1, A2, and A3. So let's do, which one should we do? Let's do the even ones, 12. So essentially what you want is, you can write it as a vector equation and solve for it, but you're really just solving for a system, or, you know, so why don't we just write it as a matrix and try to solve for it that way? Because if we can write this into a matrix, then we just row reduce and then see if we can have any solutions. And again, the relationship between the system of linear equations, the vector equation, and the matrix is just looking at each of these vectors as columns of the matrix. So let's do that. 1, -2, 2, 0, 5, 5, 2, 0, 8, and then your augmented part is -5, 11, -7. So now let's go ahead and row reduce to see if we can have any solutions for this, because we're solving for x1, x2, and x3. It looks like I can do a couple of steps in one. I'm going to use my first row and manipulate the second and third rows. So I'm going to keep the first row the same. And then I want to say, I think I want to multiply row 1 times +2 and add it to row 2. And that would get rid of my first element in the second row. So what else do I have after I do that? So 0 and 5, I have positive 2, that's 4 and 0. And negative 10 plus 1, or plus 11 is equal to 1. All right. So I'm going to do this in one step. But, you could rewrite the whole matrix and then deal with a third row, but I'm just going to go ahead and do this in one step. It looks like if I multiply the first row by negative 2 and add it to the third row, I can wipe out that first element as well. So that goes away. We have 0, and then I can, what did I say, multiply the first row by negative 2 and add it. Multiply the first row by negative 2, that's negative 4, add to 8. And then multiply the first row by negative 2, that's positive 10. Positive 10 minus 7. Okay. Now, if I do that one more step to try to clean out the bottom and to write it in row echelon form, it looks like I can multiply the second row by negative 1 and add it to the third row. And then that looks like it's going to wipe out the first two and then make the last one non-zero. So I have 102, negative 5, 0, 5, 4, 1, 0, 0, 0, and it doesn't really matter what this is, but I suppose we should figure it out. Positive 2. Wait, you with me? I was looking at you guys, and you guys are all on board. And yeah, is it cool? All right. So, what do we have here? No solution. So we have our last row, 0, 0, 0, and then the augmented last row is 0, 0, 0, and then you have a non-zero element. And then so if you were to translate that back into a system, you're going to have 0 is equal to 2, which is no solution, which gives us no solution. So what they're saying here is that you cannot write x1 times a1, 1, negative 2, 2, plus x2 times a2, 0, 5, 5, plus x3 times a3, which is 208. And you can't find any values for x, y, and z to make this equal to minus 5, 11, and minus 7. So no values of x1, x2, and x3 will get your b vector. Okay. Well, that was interesting. That was kind of exciting. Were you excited? Yes. This is me excited. All right, questions? Good. Well, I mean, it's good if you don't have any questions, but if you have questions and you don't want to ask, that's not so good. All right, good questions. Let's see. X1 and X2. So X1 and X2 and X3 are the scalars that we're looking for. We're asking ourselves, can we scale these three vectors so that they can somehow get to negative 5, 11, negative 7? And the answer is nope, can't do that. We'll talk about, there's this interesting geometry behind this also, so we'll talk about that in a minute. Did you have one? Okay. Let's you're curious about what? Oh, the application. Um, I don't know. You have to ask your physics teacher. Sorry, I'm sorry. Uh, I'll come up with applications later. Yeah, Jessica. Okay, so you took Calc 3, right? For those people that took Calc 3, we're going to take a look at this in 3 dimensions. We're going to get a visual of this, and we'll see what this means graphically. And so this will be an interesting picture to look at because it's in 3D. Hold on, Chris. We are. We're looking for the weights x, y, x1, x2, and x3 are the weights. And that's exactly what we were trying to solve for. Yeah, so they don't explicitly say we're looking for the weights, but whenever we're looking for the constants, the coefficients in front of these vectors, we're essentially looking for the weights. Okay? Yeah, well, you're kind of ruining my thunder, but yeah, yeah. So in 3 dimensions, geometrically, these are three vectors in 3D, right? But they only work on a plane. So these three vectors are actually on the same plane. And apparently this other vector, -5, 11, -7, is a point that's not on the plane. And so these three vectors have no way to try to get out of the plane because they're all on the plane. You know what I mean? Whoa. See, I got a little excited there. But well, again, we'll see if we can do the picture. Chris. Correct. Yes. So the left-hand side is a linear combination of those three vectors, and B is a vector that you're trying to get at from those other three vectors. And what we've just shown is correct. B is not a linear combination of these three vectors. All right. Since we're here, let's take a look at the graph now. All right. Um, is there a view? 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 What's going on? It's from the textbook. I think it's number 12. All right. Well, So what we have here is 3 vectors and a point. And what we're trying to look for is a way to get to that point. Now, it's kind of hard to look at, but if anybody has taken Calc 3 already and would like to try to find me the equation of the plane that these 3 vectors are on, you only need 2 vectors. We can do a cross product, but I don't know how. I don't know how to do a cross product on this program. So it looks like it's really close to that plane. So it looks like these 3 vectors are coplanar, which means they all lie in the same plane. And it looks like that point is close to that plane, but not quite on that plane. Let's use the ones with 0, 5, 5, and 2, 0, 8. So we can use a combination of any of those vectors, and you do the cross product, you get a perpendicular vector and all that stuff. But yes, even better, right? Don't say that. What is it? 4? And then there's a minus here? No. Oh, I have x. I need an x. It looks like it's on there. Well, it's a little bit off. Yeah. So you can go ahead and put minus 5 in here. And then put 11 here. And put minus 7 here. Yeah, so this thing is supposed to be equal to 0, but it's not. And so, although in the graph, it looks like it's on it, it's really close, but it's actually not on the plane. Well, we can zoom it and we can adjust the x's. We're probably messing around with this way too much. Never mind. Let's just. Anyways, so the geometry behind that is that those 3 vectors actually span a plane. In general, if the 3 vectors span a plane, then that means the 3 of them are all, well, I was going to use this term called linearly dependent, but the idea of dependence is something that we're going to cover a little bit later on. So we'll just skip over that. So anyways, for this particular problem, we're interested in finding constants, the weights I guess I'll try to start using that word. We're trying to find the weights for A1, A2, and A3 so that the linear combination of that would equal to B. And in this particular problem that we did, it didn't work. Okay. So let's look at the span, the idea of a span. We're going to keep talking about linear combinations and spans. And so the idea of a linear combination is important. The idea of span is going to be important for us as well. So if you have a set of vectors, here they say V1 through Vp, and these are vectors in Rn, then the set of all linear combinations is called a span. So this is probably the more appropriate place to set up that grid, that slanted grid, to describe what the two vectors might cover or what the three vectors might be able to cover. All right. So let's take a look at the same two vectors that we were working on at the very beginning. And let's try to imagine what's in the span of this of these two vectors, u and v. So the span is going to be all the linear combinations. We can say linear combinations, or we can write mathematically C1 times the first vector plus C2 times the second vector. So the span can be all the vectors that can be written in this form. So now the question is, what is that? Can we describe that? So we know we're in R2. And so the question is, I guess a different question would be, can we find a point in R2 or vector in R2 so that the span does not hit that point? Okay. A couple of people are shaking their heads. Did you have your hand up before I said that? Oh, okay. So a couple of people said no, and how can we prove that? Well, we can not proving it directly, but maybe we could just do an example. Let's make up a point in R2. So let's let B equal to, I don't know, give me a point. Like, no, I mean, we can make it general, but let's 1, 1. Really? 0, 0? No. I know. I thought you guys would be a little bit more creative. No. 3 and 5. So let's say we have 3 and 5. If this spans everything in R2, which the two people who shook their head are claiming, then that means I should be able to find weights for u and v so that I would get 3 and 5, right? So let's bypass the vector equation. Let's go straight to the matrix because they're all equivalent. -1, 2, -3, -1. So remember that the columns of the coefficient part of the matrix are just the vectors. And then the augmented part is what we want to get to. We want to get to 3, 5. And so can we find a solution for this? Let's see. Yeah, that's it. I was trying to remember. Multiply it by what? By 2? First row, and add it to the second row. And then so 2 in the first row is -6, -1 is -7, 2 in the first row is positive 6, and that's 11. Okay, so we're going to have x2 is equal to negative 11 over 7 if you solve for that. And then x1 is going to be whatever. I don't want to solve for it. If I just wait here for a minute, somebody will solve for it for me. La, 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 la. It would be like 33 minus 21 or something. 20, positive, negative. Anybody? Anybody? What? 54 over 7? Wow, that's more than I thought. Anyways, the point is we get a solution. Really? Nobody else can do it? You guys can work fractions. What? All right. $12. Nobody's. That's a good goal. Yeah, if I don't give you any like solving linear equations by hand, then that means all the questions would just be theoretical. How about that? You want to sign a deal with the devil for your grade? Anyways, we get a solution. In fact, Nate was alluding to the idea of just saying instead of this particular 3, 5, what if I generically put xy here? Can I put xy? Yeah, put xy, or I can put a. Actually, this should have been C1 and C2 because that's what we denoted as the notes, as the weights. Anyways, we can generically have put B1, B2 for the B vector and then try to solve for it, and we'll see that we're always going to get a solution. Even if we had 0, 0 or 1, 1 or some of those other ones that you guys were throwing out, we can always find a unique solution for this particular system. Okay. So if those two vectors are pointing along the same line, then any linear combination will be stuck on that line. If they're parallel, same thing, right? If they're pointing in, or even opposite direction. So if they're opposite direction, pointing in the same direction or opposite direction, that means they're scalar multiples of each other, and that means they're going to be stuck on that line. So that's actually an interesting thing to look at. I think I was going to look at that later on. Yeah, so let's do a quick example then, since we're continuing to talk about it. So let u equal to 1, 1, and let v equal to 2, 2, for example, right? So this is an R2, so we can draw this in 2 dimensions, and then we have the 2 vectors. looking like this. Now, any linear combination, so first of all, let's think about that slanted grid again, right? If we had a slanted grid on this example, then our slanted grid would look like this. That's pretty boring, right? It doesn't fan out to anywhere else. It's a slanted grid, but they're all along the same line. Okay. Second, if you have a point outside of that line, there's no way you can scale either of these two vectors and add it to the other vector to get out of that line. Okay. So this is a case where these two, the span of these two vectors would just be every single point on this line and nothing else. Span of u and v is going to be the line. And I made the line to be that 45-degree line so that I can just write x equals y. Okay. So the definition says a span is equal to any linear combination of the vectors that are involved. So I can scale this, but when I add these two vectors, they're always going to be along the same line. Okay. All right, so I have a couple more problems here, but let's skip over that. Yeah. Everything that grid can cover is the span of those two vectors, correct? Yeah, because when you think about scaling them, you're putting vectors on top of each other, and then when you're adding them, then you're combining these vectors. So going back to that picture again, we can say that these two vectors, the original two vectors that we started with, actually span something. Now, in that example where we're restricted to that line, it only spanned that line. What can you say the span of these two vectors are? So this thing spans all of R2, which means I can pick any point in R2 and I can hit it with these two vectors. Yeah. Every time you get two lines that are not parallel. So this, we can safely say now, spans all of R2. Okay? In 3 dimensions, we could talk about spanning a line in a plane also, or you could span the whole space. You can span all of R3. Well, 3 vectors that are, yeah. So remember, we had 3 vectors, but those 3 vectors were all in the same plane, and they didn't span all of R3. So we need one of those vectors to be just a little bit off, so that now we can get anything that we want in 3 dimensions. No, if 2 are parallel, you could put them together to be the same vector, and then you'll only still span a plane. So that still could happen. So we just want 3 of them to be totally different. Right, and then, yes, only in the direction. Right, yeah. So that idea is called linear independence. And again, we're going to talk about that later. All right, let's jump to this matrix times a vector business. Let's think take a look at how they define it. The way they define it is kind of weird, but let's see if we can try to get an understanding of it. It's weird because they always bring down the matrix into a set of column vectors. And so that's one thing I realized when I was teaching this last semester is that I keep wanting to define it using a big matrix, and then they have certain ways to define that with the subscripts and stuff. But here they want to define it using column vectors. So I'm going to see if I can present it that way. So a matrix can be seen as a set of column vectors like we've been looking at already. And we can imagine that matrix A is a set of column vectors. And then we can imagine X. Now this is X, a vector X in Rn. Now I want to just say that this vector X, since it is a vector, it could be written as a collection of scalars, a column of scalars, and it itself can be seen as a column vector. Okay, so that's what happens here, is that A, the matrix A, can be seen as a matrix of column vectors, and then your vector X is just another vector in Rn, can be seen as in itself a column vector. Then we could take the product of this, a product of a matrix and a vector. So the product of the matrix and a vector is going to be defined, well, the working definition works out the matrix times a vector, and then it just boils down to this. Okay, yeah. The weights are seen as components of a vector. The weights themselves are not vectors, like separate vectors themselves, but all, yeah, they went into X instead of C's, right? Yeah, so it used to be C's and we used to weights, but they're the same thing. They're weights. That's why I don't know about the word weights still. Does correspond to a column. Yes. Yes. 4, 3, 7 together is a vector, but 4 itself is not a vector, it's a scalar. 3 itself is not a vector, it's a scalar. Right? 7 itself. So these by themselves, they're sitting here by themselves. They're scalars. And in the previous definition, they were the weights of our linear combination. Four zero zero or 437, that together is a vector. Yes. So if we follow their recipe in defining this product between a matrix and a vector, we would take the elements of our vector and use them as weights, and then multiply each of those by each column in that vector. So what does this end up? This ends up being 4, 0 plus 6, negative 15 plus minus 7. That's a 3, right? 21. And then 4, 6 minus 7, 3, and 0, 15, 21, 6. So my result here is a vector and the result is 3, 6. Yeah. We're multiplying a matrix times a vector. So we're multiplying a matrix times a vector. Each column of this matrix is a vector. And so it becomes a multiplication between an element in the second vector times a vector from the matrix. The number of columns here has to match the number of elements in that vector. Yes. Okay. It's weird, huh? So a matrix is just a collection of numbers that describe a system of linear equations. Okay, so I don't know if anybody's ever done matrix multiplication before or have worked with matrices before, but matrix multiplication in general can seem a little easier than this. It's a matter of multiplying a row times a vector, and then getting your results, and you're kind of taking the dot product of it. So again, this approach is a little bit different from what I'm used to and what people have seen as matrix multiplication may be used to, but we're going to try to stick with this idea of dealing with each of these matrix as just a set of column vectors. Yeah. So showing you the other way would be would require some knowledge about the dot product. So I would say the answer to this is dotting 1, 2, -1 with 4, 3, 7. So 1, 2, -1 dotted with 4, 3, 7. And this is 4 plus 6 is 10. 10 minus 7 is 3, right? And then now I take the second row and then dot it with this. So 0 minus 5, 3, dotted with 4, 3, 7. And then I have 0, negative 15, plus 21. So it's the same numbers that I got. Okay. All right. So what was I saying? Quiz on Monday, and then I'm gonna have you guys work with MATLAB or some form of MATLAB. And so if you're familiar with FreeMat or Octave, those are two possible things to download. Or if you have MATLAB yourself, that would be great. I'll post some videos about acquiring these things, and so you can start messing around with it. And then I'll formally assign some worksheet problems dealing with this. You? No. The quiz on Monday will probably reduce a 3x3 or a 3x4 matrix or something like that. So I'm gonna say no on the calculator for that. And then after you've proven to me that you could do the row reduction, then calculators will be okay later. You'll probably be mainly using it out of class, but I might use it in class as demonstration. If that can be arranged, yeah. So these computers out here have MATLAB, so we can do that. Yeah. If we do this in class. All right. Have a good weekend.